Hello, and welcome to Beyond the Burn, a journey into the surprising chemistry that underpins our entire world. When you hear acid or base, what first springs to mind? Perhaps the sharp, invigorating tang of lemon juice, or the distinctive slickness of soap, maybe even the ominous bubbling of a chemical experiment. For most of us, these concepts are reduced to simple labels: corrosive, neutralizing, or even just dangerous. But beneath these readily observable interactions lies a universe of elegant, fundamental chemistry, far more intricate and ubiquitous than most of us ever realize. Acids and bases aren't just about extreme reactions. They are the unseen architects of life, crucial industrial processes, and even the very geology of our planet. Their influence permeates every aspect of existence. Consider the precise pH balance of our blood, a delicate equilibrium absolutely essential for our survival. Think of the colossal mountains slowly shaped and eroded over millennia by the relentless, subtle power of acidic rain. For centuries, humanity has grappled with defining these powerful substances. Early chemists relied on sensory observations. Acids typically tasted sour, corroded metals, and turned litmus paper red. Bases, conversely, tasted bitter, felt slippery, and turned litmus blue. While these empirical distinctions were a crucial starting point, they were much like only seeing the very tip of an enormous submerged iceberg. The true surprise in acid-base chemistry begins when we explore how our scientific understanding has profoundly evolved, revealing layer after layer of chemical sophistication. Prepare to have your fundamental perceptions of these everyday chemicals profoundly reshaped.
Our initial descriptions of acids and bases, while useful, were limited. The first significant leap came in the late 19th century with Svante Arrhenius. He proposed that acids produce hydrogen ions, H+, when dissolved in water, and bases produce hydroxide ions, OH-. This definition elegantly explained neutralization as H+ combining with OH- to form water. Think of hydrochloric acid releasing H+ in water, or sodium hydroxide releasing OH-. It was groundbreaking, but restricted to aqueous solutions. The 20th century brought an even broader perspective. Johannes Bronsted and Thomas Lowry independently proposed that acids are proton, H+, donors, and bases are proton acceptors. This dramatically expanded the definition beyond water, introducing the concept of conjugate acid-base pairs. For instance, ammonia, NH3, can accept a proton to become NH4+, acting as a base even without hydroxide ions. This definition allowed us to understand acid-base reactions in a vast array of solvents and gas phases, revealing previously hidden relationships between molecules. But the story doesn't end there. Gilbert Lewis pushed the boundaries further in 1923, defining acids as electron pair acceptors and bases as electron pair donors. This radical idea decoupled acid-base chemistry from protons entirely. A classic Lewis acid is boron trifluoride, BF3, which can accept an electron pair from an electron-rich molecule, like ammonia. This definition is the most encompassing, explaining phenomena like the formation of complex ions and reactions involving metal catalysts, which have no protons to donate or accept. The evolution from Arrhenius to Bronsted-Lowry to Lewis reveals increasingly sophisticated ways of understanding molecular interactions, a truly surprising journey from the simple to the profoundly abstract.
With these increasingly sophisticated definitions, we gained a powerful tool for measurement: the pH scale. Invented by Soren Peter Lauritz Sorensen in 1909, pH, meaning power of hydrogen, is a logarithmic scale, ranging typically from 0 to 14. A pH of 7 is neutral, like pure water. Values below 7 are acidic, and values above 7 are basic. Crucially, because it's logarithmic, each step represents a 10-fold change in hydrogen ion concentration. A solution with pH 3 is 10 times more acidic than one with pH 4, a concept often underestimated. This delicate balance is nowhere more critical than in biological systems. Our blood, for example, must maintain a pH very close to 7.4. Even a slight deviation can be life-threatening, disrupting enzyme function and protein structures. How does the body achieve this astonishing stability? Through buffers. Buffers are solutions that resist changes in pH when small amounts of acid or base are added. They typically consist of a weak acid and its conjugate base, or a weak base and its conjugate acid. These pairs can mop up excess H+ or OH- ions, maintaining a stable pH. Imagine a chemical tug-of-war, where buffers constantly pull to keep the equilibrium. From the carbonic acid bicarbonate system in our blood, protecting us from metabolic fluctuations, to the careful regulation of pH in fermentation vats for brewing and pharmaceuticals, buffers are unsung heroes. They're essential in agriculture to optimize soil conditions for crops, in environmental science to understand pollution, and in nearly every industrial chemical process where precise control is paramount. The elegant simplicity of pH measurement, coupled with the ingenious action of buffer systems, truly highlights the surprising intelligence built into chemical equilibrium.
Our exploration has revealed that acids and bases are far more than just corrosive liquids. Their chemistry extends into realms far beyond the aqueous solutions we initially considered. What happens when we venture beyond water? In non-aqueous solvents, the relative strengths of acids and bases can shift dramatically, challenging our conventional understanding. For instance, acetic acid, a weak acid in water, can become a strong acid in liquid ammonia. The solvent itself plays a crucial role, often acting as a Bronsted-Lowry acid or base, influencing proton transfer. Then there are the extremes, superacids and superbases. Superacids are stronger than 100% sulfuric acid, capable of protonating even hydrocarbons, substances we typically consider unreactive. Think of magic acid, strong enough to dissolve wax candles. Superbases, conversely, are extraordinarily effective at deprotonating very weak acids. These extreme chemicals are not just laboratory curiosities, they are vital tools in organic synthesis, catalyzing reactions that would otherwise be impossible, allowing us to create complex molecules with precision. Acid-base chemistry is also at the heart of catalysis, where these substances facilitate reactions without being consumed themselves. From the catalytic converters in our cars neutralizing harmful emissions to the enzymes in our bodies driving metabolic pathways, acid-base principles are fundamental to speeding up chemical processes. On a global scale, however, the balance can be disrupted. Ocean acidification, caused by increased atmospheric CO2, poses a grave threat to marine ecosystems, as CO2 dissolves in water to form carbonic acid, altering the ocean's pH. Acid rain, another consequence of industrial emissions, damages forests and infrastructure. The surprising chemistry of acids and bases, therefore, is not just an academic pursuit. It is a profound force with immense implications for technology, life, and the very future of our planet. Subscribe to the channel and hit the bell icon for more amazing videos.